Well, you might be wondering, what happens if we just pick strategies randomly? Well, that doesn't seem to get us anywhere. I mean, how could random strategies give you anything predictable or deterministic? That can't happen, can it? Oh, yes. Oh, yes, it can. And this is a very cool idea. Let's see how this works. Let's assume that players choose a strategy at random based on some probability distribution. So let's say A has 4 different strategies it can choose. It does the first one 25% of the time. It plays the second one 40% of the time. It plays the third one 25% of the time. And the last strategy only 10% of the time. Now notice those numbers add up to 1. That's good. Likewise with B. B chooses some percentages, 10%, 20%, 30%, 10%, 30% for its 5 strategies. Again, having these numbers add up to 100%. Given those, then what do we do? What's the expected payoff that you get from playing over and over and over at random with these probabilities? Well, let's think of a specific case. Let's say player A plays the second strategy very frequently, 40% of the time. And let's say player B plays the fourth strategy infrequently, only 10% of the time. How often does it happen that you have both of these events happening? Player A plays strategy 2, player B plays strategy 4. Well, you have to multiply these probabilities together. That's 10% of 40%. That is 4% of the time this happens. Now, what is the expected payoff? Well, if I look at this entry in the matrix, then I get an expected payout of 3 times the probability that that event happens. That's 3 times 4%. That's an expected payoff contribution of 0.12. Now that's for one particular pair of events. What happens in general? Well, let's think about this. This might seem complicated, but a little bit of linear algebra is going to help us out a lot. Let's use vectors to encode these probabilities for playing different strategies. So player A has a vector of probabilities for its m different strategies, A1, A2, A3, all the way up through AM. Now, we have to make sure that those numbers add up to 1. These are all numbers in between 0 and 1. Gotta add up to 1. That's player A. Player B does the same thing. Player B has n strategies and a vector of probabilities, B1, B2, all the way up through Bn, all those numbers adding up to 1. The expected payoff is computed just like that previous example, where we do it for each AIBJ combination using the PIJ entry of the payoff matrix. When we add all those up, it seems kind of complicated, but in the language of linear algebra, it's so easy. The expected payoff is A transpose times P times B. A little matrix vector multiplication goes a long way. And now we have something that we can work with. And the question that we are left with, is there an optimal random strategy? What choices of probability vectors A and B maximize A's expected payoff, maximize B's expected payoff? Now we can get started.